Welcome to our NPTEL courses on advanced power electronics and the control. Today first we will discuss with the isolated DC-DC converter, that is the remaining part of the isolated DC-DC converter. We have discussed half bridge configuration, we have discussed flyback, thereafter we have discussed the forward, thereafter we have discussed the push pull, and we have discussed also the half bridge, and then we shall do the another topology, that is called the full bridge. Then we shall switch over to the DC to AC application. Essentially that will be the inverter application, and we know that there will be two kind of inverter, that is VSI, voltage source inverter, and current source inverter, and different kind of PWM technique associated to it. Okay, let us start. So, these configuration we have discussed in our previous class. We have we just little bit of recap that it is a half bridge configuration. So, since you are doing the bucking operation, so being essentially you get the half of the voltage, and also you can control over the trans ratio, as well as you can actually have a duty cycle. So, you have a multiple advantages once you are bucking through the half bridge converter. But one essential disadvantage of it is that sometime there might be mismatch between these two switches. So, this small mismatch over a period of time may actually lead to the saturation of this transformer, because of that there will be a average DC in every cycle, and that will be accumulated over cycles, and that will may turn to this actually DC biasing of the transformer, and it will may saturate. For this reason we require to give a blocking capacitor which will block the DC part into the transformer. So, essentially this is the T on time of the IGBT or MOSFET depending on the rating, and nowadays actually high bandwidth devices are coming like SiC GaN devices. So, this rating can go high to the 3 times more, as well as the switching frequencies. So, again it is the second PWM, and we have actually the Vp that is across this transformer, that is V in by 2, and accordingly this area has to be matched with this area, that is the essential purpose of it. And the current through the switches R is essentially from Q1, then actually the diode conducts for the period. When it is off, we assume that continuous conduction mode, and thus this region actually current drops into the circuit. Please remember that in power electronics, positive ramp is associated with the switch and negative ramp associated with the diodes. So, this is the time where actually diode conducts, and also in this case you can see that diode D3 and D4 conduct depending on the different criteria, and this is the current to the inductor, and we will have a ripple, thus ripple will be suppressed by this capacitor. So, what essentially you get here, what is the advantage over the other topologies, that is actually we have discussed flyback, thereafter we have discussed the forward, thereafter push pull, then it is this. One of the advantages is that its power handling capability can be very high, because you can actually there is no concept of resetting flux, you are resetting flux in every cycles, and thus we need not have to have a resetting winding, and stresses across the switch also will be low. Now, let us see that the advantages of this half bridge converter. Half bridge converter is a transformer isolated converter based on basic forward topology, that is actually dots are at the same point of the forward topology. The one leg of the converter is formed by switch Q1 and Q2, and remaining half of the converter is formed by C3 and C4. Therefore, it is called a half bridge converter. Q1 and Q2 creates a pulsating AC to the transformer. Primary transformer is used to step down mostly of the pulsating primary winding voltage, and also provide isolation between the input and the output. During steady state condition, C3 and C4 are charged to the equal voltages, so that this junction C3 and C4 carry half of the input voltage potential. So, that is something you require to remember it. So, these two voltages are equally divided, otherwise you have to provide the potential divider network by connecting a small resistance in series with them. So, what you can do here, when Q1 is on, the dot end of the transformer is connected to the positive V in as switch is on, and the voltage across actually C4 is applied to the transformer primary. So, half of the input voltage is applied to the winding when it is actually Q1 is on, and that is the positive half of the cycle. In this mode, D4 becomes reverse biased and D3 becomes forward biased, which carry the full inductor current through the winding 2 for the winding NS1. Difference between scaled input applied voltage to the secondary 2 than output voltage is applied to the inductor in the forward direction. Therefore, the inductor current IL rises linearly from L1 to L2 within a limit prescribed by the designer. During the mode, the sum of the scaled secondary current and primary current flow through the switch Q1. This mode starts with end of T on period. In this mode, Q1 is turned off till end of the switching cycle Ts. Q2 is turned on after half of the switching period Ts by 2. Therefore, during T off period, for some of the both of the switches are off as shown in the waveform. When Q1 is off, body diode of Q2 provides path for the leakage stored in the transformer primary, and D4 become forward biased. As D4 become forward biased, half of the inductor current flows through D4, NS2, and the other half of the inductor current flows through D3 and NS1. Therefore, equal and opposite voltage is applied both the transformer secondary winding, assuming both the winding have the same number of turns. As a result, the net voltage across the secondary becomes 0, and it maintains the flux flow conditions. And this is the second mode, is a mode 2. Output voltage is applied to the inductor in a reverse direction when both the switches are off. Therefore, inductor current decreases from L2 to L1. Body diode of Q1 and Q2 provide path for transformer leakage energy. After Ts by 2, when Q2 is turned on, dot end of transformer primary is connected to negative of V in. Input voltage is applied to the transformer primary in reverse direction when Q2 is on. To avoid magnetic saturations of the core, let us assume the number of turns of NS1 and NS2 are the same and turn on period of both the switches are same. After T on, the period Q2 is turned off till the value complete the duty cycle, that value corresponds to Ts. So, what is the advantage? Advantage over the predecessors, these are flyback, forward, push pull. You will find that magnetic core is small, so you can actually in a same size you can handle big amount of power handling capability, thus energy density is more. No air gap in the magnetic path, so designing of this transformer is much easier than the flyback. Less stray magnetic field because you are resetting the actual magnetic field by standing on the Q1 and Q2. Disadvantages, this is not disadvantage, we must say it is limitation, their functioning half of the supply potential, where switching transistors are proportional to 2 times of the collector current as comparison to the basic push pull scheme. So, this is the one of the things you have to keep in mind, the rating of the switches. And we will discuss little later, it is not suitable for the current mode control. Current mode control means actually there are two kind of current mode control we have already discussed. One is peak current mode control, another is average current mode control. So, in this current mode control it cannot be operated. So, it will be most suitable for the voltage mode control. Now, let us see the full bridge configuration. In these configurations actually it will be replaced by the force switch, thus actually when Q1 and Q2 is on, then actually current flows this way, when Q3 and Q4 is on, current flows in this way. So, it is a normal transformer operations or the inverter operation. So, what happened here, it is quite simple in the sense, and it has the maximum power handling capability, and what happened here, the transformer gets the whole voltages, and thus you can have a better utilizations of these voltages, and mostly this is applied for the high power applications, and core is the smallest considering the kVA rating of the transformer. And here what happens generally, this kind of, since we have reset all the problem while starting, we have said that isolated DC to DC converter has few drawbacks. We have to mitigate drawbacks by taking a proper action. First of all, we have to reset the flux. Since we cannot use DC in transformer, there since you have a incorporated a DC a transformer into it. So, you have to see that in every cycles, high frequency cycles, flux get resetted. Here you can reset the flux, and since C1, Q1 and Q2 conducts, there will be a gap where diode will conduct, and thereafter again Q1 and thereafter Q3 and Q4 conducts. So, automatically flux will reset in all the places, and it has a huge rating. It actually it can handle the rating same as the of the supply voltage. So, another aspect is that actually switching stress across the devices, since both the switches just opposing this actually this voltage. So, voltage stress across the switch is minimum compared to this all other circuit where you have employed the resetting circuits, and also here you will get maximum power. Here you get, instead of the V in by 2, here you get total V in. So, these are the few advantages, and thus what happen. So, once you have actually reduced the rating, voltage rating of this actually transformer, automatically you require to increase the current rating of the switches. That is one of the drawback of the half bridge converter, because here you get V in by 2, automatically the instead of I1, the I2 current will 2I current will flow. So, current rating has to be current handling capability to have the same power rating, power handling capability of those device required to be doubled, but here current handling capability of the device is half compared to this half wave half bridge converter. So, these are the few advantages of the full bridge converter. Let us analyze it, very simple to analyze. So, once actually you have T on and T off, consecutively pulses will be there. So, you will get this voltage, and you can see that your stress across the voltage is V in. Please note that actually once it is off, it is blocking the voltage, that value equal to basically the input supply voltage, and this is the inductor current, output inductor current here, and we assume that this actually the current is continuous, and please note that these two switches both jointly blocking the voltage B. So, stress across the individual switch will be the half of the voltages. So, a full bridge transformer is a isolated buck converter. So, you can buck the voltage, since you cannot increase the duty ratio more than 1. The basic diagram of the waveform is shown in the actually the previous slide. As per the schematic diagram, the shape of the full bridge converter looks like the H and for this is called it is H-bridge converter. Basic operation is almost same. Transformer primary is connected between the two legs and by the switches Q1 and Q4, and another is Q3 and Q2. All the switches creates a pulsating AC transformer. Primary transformer is also used to step down pulsating voltage as well as to provide isolation between the input and output. Unlike half bridge topology, in full bridge topology the voltage applied on transformer primary when either of the switches is on is half of the input voltage with twice of the switching current. Where voltage stress of the switch is twice of the input voltage. So, this topology is not suitable for high power or actually around 500 watt. So, that is the one of the actually consideration we have to keep in mind. Q1, Q2, Q3, Q4 switches alternately selected for the switching period. So, mode 1 when Q1 and Q2 is on for the period T on, dots at the end of the winding becomes positive with respect to the non dot end, and in this mode D4 becomes reverse biased and D3 becomes forward biased, and D3 carries the full load current through the transformer a secondary winding of NS1. As this mode of the voltage is applied across the transformer primary, the switch carries the reflected load current as well as the transformer primary magnetizing current. So, this will carry both the current. The difference between primary winding scaled voltage and secondary winding output voltage is applied across the inductor as it is same in case of the half bridge converter. So, mode 2 is almost same, just we have to have another pair of switch. So, at the end of the period switch Q1 and Q2 are turned off and remains in the state till the rest of the switching period of Ts, and in this mode Q3 and Q4 are turned off after some delay, because you want actually a diode to conduct, because even if you get the pulse unless current does not decay. So, another pair of switches will not turn on. So, after half of this switching period Ts, this mode Q3 and Q4 are turned off after half of the switching period Ts by 2. During T off period, all the switches are off for some interval of time. When Q1 and Q2 are off, the body diode of the pair of the switches Q3 and Q4 provides a path of the leakage energy stored into the transformer primary. So, diode will conduct. So, what will happen once actually Q1 and Q2 is conducting, then unless you trigger Q3, Q4 till that time, the body diode in case of the MOSFETs or the anti-parallel diode in case of the IGBT connected to the opposite pair will take care the conduction and it will demagnetize the magnetic circuit. So, this is the one of the features, please keep in mind. In this mode, the output rectifier D4 becomes forward biased and it is carrying the half of the inductor current through the transformer secondary winding. Another half of the inductor current is carried by the diode D3 through the transformer of secondary winding NS1. Therefore, net voltage applied across secondary during T off is 0, and this keeps the flux density of the transformer constant. This is the way actually full bridge transformer, full bridge converter works. And after Ts by 2, when actually the same, it is same as actually the initial stage, when Q3 and Q4 was on, the dots end of the primary or the becomes the negative with respect to the non dot end, and in this condition D3 becomes reverse biased and D4 becomes forward biased. So, D4 carries the full current through secondary windings of NS2. As input voltage is applied across the transformer 1, switches carry scaled current with the primary magnetizing current. As input voltage is applied to the transformer in reverse direction, flux density core changes from final to the initial value. The difference between primary scale voltage to secondary scale voltage and the output voltage is applied to the inductor L in forward direction. So, assuming that the secondary winding turns is basically NS1 and NS2 are the equal, to avoid the magnetic saturations of the core, T1 period Q1 and Q2, Q3, Q4 are kept same. So, this will ensure the resetting of the flux. So, if actually this is the Ts time, we just drawing on the same in a positive y axis, Q1, Q2 if conducts, and this is basically Ts by 2. You can start, thereafter there will be a delay, and this actually ratio and this ratio required to be same to reset the flux. After T1 period, Q3, Q4 is remains off till the time Ts. This is the time interval. During switch on period of the pair of the switch of the switching stress over the other pair of the switches of the entire voltage V in. So, V out and V in relationship. Here you will find that assuming this continuous conduction mode, if it is otherwise stated, the relation between the input and output voltage is same, basically 2 V n into D, where D is T1 by T Ns by Np. So, you can actually play with the trans ratio and get the desired output voltage. So, what is the advantage of it? It is the simplest in operation, and you have 4 switches, stress across the switches is less. You have a control over the controlling the duty cycle, so that you can actually actively reset the flux, and you have actually highest power density. So, size of this full bridge converter will be least than the other. So, advantages are full bridge is used in application for the high voltage requirement. Mostly this finds applications in offshore wind turbine. So, you may have actually a seashore in a isolated island. From there actually you can put a huge windmills or wind farms, and of course it may be DC, and you wish to transfer this DC from that wind shore to this actually the mainland. So, you can use this kind of DC to DC converter, and then actually instead of the stepping down, you may actually essentially step up and you will feed to the HVDC line sometime. Full bridge has slightly more voltage ripple than the half bridge. This is actually one of the problems. So, you will find that actually it will be to smooth out the ripple, it will be little bulky. Full bridge uses 4 diode in places of just clipping of the half wave. It changes the polarity of the half wave. Now, let us take the disadvantage of the full bridge. Of course, the component count is maximum. You use the 4 active switches. Though the cost of the switches is drastically coming down, then of course, that logics is gradually get negated, and you have a derating of the passive devices, and you expect that actually the switches will last longer, and thus the component count cost has been not at all a disadvantage now. So, since there is a losses across the 4 active devices, 2 active devices always, so efficiency of this kind of topology will be less. The bridge has an efficiency of 95% since it employs actually the 4 switches or the 2 switches consecutively. and the half bridge can have a efficiency in 99% for SI6 devices, GAN devices, as well as the actually soft switching when it is done by ZVS or ZCS. Therefore, actually the half bridge is slightly more efficient than the full bridge, but power handling capability is maximum in case of the full bridge. Full bridge electrical converter is analogous to the half bridge converter. However, it has an extra segment attached to the ground point to the load. So, we have a extra elements that is connected. Full bridge would have larger loss and the noises than the half bridge. As a result of the full bridge converter has the more switch and the element. This is the overall discussions of the isolated DC to DC converter. So, we have discussed first fly black, and it has a power handling capability is around 100 watt, and if you see the switches, it is one switch, and efficiency in the range of 80%. So, it is the simplest circuit, it uses one circuit, but this is the cause, and power density is less. Then next comes into the picture is your forward converter. So, it can go up to 500 watt. Single switch and efficiency is little higher because transformer there is actually a normal transformer. So, you can expect around 85% efficiency, and thereafter it comes to the push pull, but it uses two switches, and here this can be as high as 10 kilowatt. So, thereafter you have half bridge and full bridge. This can handle the power around hundreds of kilowatt if properly designed. It can handle the power in the megawatt, and efficiency is actually 99%. Maximum efficiency you will get in case of the half bridge converter, and full bridge converter will, since it employs more component count, you will find that actually it uses, its efficiency will be little less, around 95%. This is the some comparison of DC to DC converter, and this is a matrix, and based on that you will actually choose different kind of DC to DC converter for your application. Thank you for attention. With next class I shall continue with the another very important entities of power electronics, that is DC to AC conversion, that is the inverter operations. We shall start with the voltage source inverter, thereafter current source inverter, and we will see the different aspect of the voltage source and current source inverter by different kind of PWM technique. Thank you so much for your attention.